This is the lecture covering molecular polarity for Chemistry 1. So we've started to learn about different shapes and different geometries of molecules. You've learned how to draw all these different molecules, all these different Lewis structure. We've talked a little bit in the past about polar and nonpolar bonds. Remember, the rule that we essentially use is if it's two of the same atom, it is a nonpolar bond. If it's two different atoms, it's some form of polar bond. That could either be polar covalent or ionic, but the point is that big difference gives us a polar bond. Well, there's also polar and nonpolar molecules. And it kind of comes down to the same definition. In a bond, we said a bond was polar or nonpolar based on whether or not the electrons are evenly distributed. If it's the same atom, or same type of atom, so for example, two carbons, then they're going to pull on the bonds the same. It's a nonpolar bond. Those electrons are evenly distributed. It's a polar bond if it's two different atoms. One of those atoms is going to pull slightly different on the electrons than the other one would. One of them will be able to pull more, the other one will pull less, so it's uneven, it's polar. Well, molecules are basically the exact same way. If there is a region on your molecule where more of the electrons are sitting, we say that is a polar molecule. In the same way we would have a polar bond. So water, H2O, this guy right here. You see how there's a bunch of electrons hanging around the top side of this molecule? That tells us that this is effectively a polar molecule. It is not an even distribution of electrons. Essentially what that tells us is one of our sides of our molecule is a little bit more negative, wherever the electrons are, and wherever the electrons are not, that side's going to be a little bit more positive. Alternatively, you could have a nonpolar molecule. If all of your electrons are evenly distributed, then you're going to have a nonpolar molecule. So an example of a nonpolar molecule is this guy right here. Now I know it seems a little bit weird. I know you're thinking, hey, there's a bunch of electrons around your Cl, but your carbon doesn't have any lone pairs. Well, yes, that is true. But when you look at the whole thing, all of these electrons are being pulled outwards. So in other words, there's pulls evenly in all four directions by the electrons. So when you look at the entire molecule as a whole, you essentially have this completely balanced molecule. Here's the nice thing. We're going to teach you a couple little questions to help you figure out whether or not this is a polar or nonpolar molecule. So don't feel like you're going to always have to do it by visual and guessing. We're going to teach you the rules here in just a second. When we do start looking at polarity, we use arrows to show the direction of that polarity. We would put a positive kind of symbol blended in there to show the positive side of my molecule, followed by your arrow towards the more negative side. We are never going to make you draw your own arrows, so don't worry about that, but you will have to be able to recognize them. You'll have to be able to look at a molecule like this one over here and say, okay, well, based on the way my teacher has drawn this arrow, I need to know that this side of my molecule is a little bit more positive, and that side is a little bit more negative. That's what the arrow shows. It directs us towards the more negative side. Again, remember, you're never going to have to draw your own arrows, but you might have to get used to seeing them and being able to interpret them. Okay, so here we have CHCl3. Before we start looking at the big overall molecule, whether or not it's polar or nonpolar, let's just kind of identify some bond types. I have C and H. So we're looking at this bond right here. Circle it. There we go. That bond right there. C is a nonmetal. H is a nonmetal, so that's going to tell us that it is a covalent bond. Oh, and in fact, because remember we're dealing with Lewis structures, everything we're going to be dealing with is some kind of covalent bond. So C and H, two different atoms, we know that that bond is going to be polar. If we look at the bond type between C and Cl, again, two nonmetals, that tells us it's covalent, but the fact that they're two different nonmetals tells us it is, again, polar. So I have two polar covalent bonds. Here again, I'm going to teach you the questions to ask yourself and the rules here in just a second. But you can kind of visually start to see it a little bit here. One of these sides of my molecule has more electrons than the other. So my Cl's are going to pull more of my electrons this way than my hydrogens have. So the left side of my molecule, wherever the hydrogen is going to be a little bit more positive, versus where all of my electrons are is going to be where I'm a little bit more negative. So I'm going to be a little bit positive on the left, more negative on the right. So in fact, this is going to be a polar molecule, which our rules will tell us as well, in case you can't quite start seeing that off the top of your head just yet. So we have CO2, bond type between C and O, two different nonmetals, tells me it's going to be a polar covalent. Everything we're dealing with is covalent here. But when I look at the molecule itself, you see how the bond itself is polar. So that tells us that within the bond, within this bond right here, there is an uneven distribution of electrons. The O is going to pull more than the C will. So within that bond, there's going to be a little bit of a force saying, okay, my carbon is a little bit more positive, my oxygen's a little bit more negative. But then when I look at the other side, I can say the same thing. The O on the right is going to pull a little bit more than the C in the middle will. So there's this counter arrow in the opposite direction. These two oxygens fighting in opposite directions actually cause an overall even distribution of charge. So this is going to end up being a non-polar molecule. The two rules that I'm about to teach you will help you determine whether or not your molecule is polar or non-polar. But remember, and this is really important, just because you have polar bonds does not mean you're going to have a polar molecule. And that's exactly what this slide says right here. Compound can be molecularly nonpolar, so the whole molecule can be nonpolar, but within that nonpolar molecule, there are small polar bonds. The big idea is that all of your polar bonds are going to pull evenly, kind of like in a tug of war. Both sides could be pulling equally. Now, from the center point, if I had put a little thing in the middle of the rope, this side is going to be pulling really hard, and that side is going to be pulling really hard. But at the end of the day, if everyone is equally matched, that center portion of the rope will not move. It's only when one side starts to pull more than the other will that central point start to move and eventually win your tug of war. That's represented when the electrons are not evenly represented. That's what gives us a polar molecule. When it is non-polar, everything is pulled evenly. Everything is distributed evenly. So even with polar bonds, you could still have a non-polar molecule. Here we have a third example, H2O, pretty common. When I start looking at bond types, I have H, I have an O, I have two nonmetals. They are different nonmetals, so our kind of rule of thumb tells us that's going to be something that is polar covalent, right? Everything, again, we're dealing with is covalent, but just to be thorough. So when I look at just the O and H on the left, my O is going to pull more on my electrons than my H will. My O is a little bit more electronegative. So I get a little arrow that looks like this. My H is slightly positive, my O is a little bit more negative because it can pull more electrons. When I look over at the right combination of O and H, I get another one. Looks a little bit like this. Now notice how these two arrows are not directly fighting each other. They're not opposing each other. So really what I end up with is kind of this net arrow that looks a little bit something like this. My H side of my molecule is going to be positive. My O side is going to be a little bit more negative. This is going to be a polar molecule. So not only is there polar bonds, it can also be a polar overall molecule. So here's where it comes down. If as we went through those examples, you're sitting there saying, I still can't really visualize why something is positive or negative, then don't worry about it. If it's not working for you, don't do it. Here are your rules right here. Essentially, 2 rules, 2 questions that you need to ask yourself. Here you go. If your central atom has no lone pairs, which means if there's no dots around your center atom, and everything around your center atom is the same molecule, so they're all Cl's, or they're all H's, or they're all F's, whatever. If everything is around your center thing is the same, and your center thing has no lone pairs, that molecule is nonpolar. If your center atom has no lone pairs, but different things around it, so think back to that first example, CHCl3. I had no lone pairs on my center atom, but I had 3 Cl's and then an H. That's going to be a polar molecule. There is a slight difference in pull. It's not even on all sides. So that's a polar molecule. Last but not least, if your center atom has lone pairs, 100% of the time for us, we are going to say that that is a polar molecule. That's not 100% true, but any example that we're going to deal with and any example that we are going to give you, that will be true. So if your center atom has lone pairs, you have a polar molecule. So you could memorize those 3 scenarios and how they connect to polar and nonpolar, or here's a little flowchart for you that has you ask yourself 2 questions. First off, you ask yourself if there's lone pairs on the center atom. If yes, boom, it's polar. So if you have lone pairs on the center atom, you are polar. Done. No ifs, ands, or buts about it. Doesn't matter what's around it. Doesn't matter if they're all the same. Doesn't matter if every single one is different. Doesn't matter. If you have lone pairs on the center atom, you're polar. If you don't have lone pairs of electrons on the center atom, then you have to look at your second question. Your second question says, are all the atoms attached to the central atom the same? If the answer to that is no, in other words, if 1 or 2 of them are different, that's going to be a polar molecule. You don't have an even distribution. If you have no lone pairs and everything attached is the same, that's what gives you your nonpolar molecule. It's the only way you can get it. You have to have no lone pairs and everything else has to be the same. So either memorize the situations or memorize those 2 questions. Either way, you're going to be able to figure out the polarity of all the molecules that we ever show you. So here's our first example, NH3. Notice I didn't even give you a drawing this time. That's because you have to be good at drawing these. If you're still struggling drawing out your Lewis structures, please come see us because we are going to make you draw them as well. So take a second, pause the video here, fill out the Nassau chart for NH3, get your bonds, get your lone pairs, go ahead and draw it. Pause the video, it'll pop up in about 5 or 6 seconds, and you can check your work, and then we'll work through the rest of the example. All right, so here we have our work, our Nassau table for NH3. We have 14 electrons needed, 8 available, which gives us 3 bonds and 1 lone pair. Should look a little bit like this, and in the center, surrounded by H's, everything got 1 bond. We had a lone pair left over. It can't go to any of the H's. They only needed 2 anyways, so it had to go to my nitrogen in the center. If we want to say the shape of this molecule, hopefully you've been practicing assigning shapes to your structures. It's got 4 areas total of bonding. 1 of them are lone pair, 3 of them are links. So that should tell you that your shape is a trigonal pyramid or trigonal pyramidal. Either one is right. So we have our shape, then we go to our polarity. We know the bonds are all individually polar. NH, 2 different nonmetals, that's a polar bond. So then, but separate from that, we go to our questions. First question we ask ourselves, is there a lone pair on the center atom? Well, when I look at my structure, there's a lone pair. right there on my end, my center atom. So right away, without even needing another question, because I have lone pairs on the center atom, I know that this is a polar molecule. That's it. Done. You know the molecule's polar, write polar, and let's move on to the next example. Example 2 is going to be CCl4. Same deal as last time. Go ahead and pause the video here. I'll give you about 5 seconds to pause it. And here in just a second, it'll pop back up with the work done, and you can check whether or not you can still do your nacelle. Alright, so here's our structure and nacelle for CCl4. 4 bonds, 12 lone pairs. All of my Cls have 1 bond. I have an even amount of lone pairs, 3 on each of my Cls. That gives us a total of 12. So when I go to my shape, 4 areas of bonding. None of them are lone pairs, 4 links. So hopefully, with your practicing of shapes and Vesper, you can tell me that this shape is going to be a tetrahedral. And when I look at the polarity, I ask myself my first question, does my center atom have lone pairs? Well, my center atom in this case is C. There shouldn't be any lone pairs on that guy, so the answer to that question is no. If your answer to that question is no, then you can move on to your second question. Is everything around your center atom the same atom? Well, when I look, C is in my center, I have Cl on top, Cl to the right, Cl on the bottom, Cl to the left. So everything, not only does my C not have any lone pairs, everything around it is the same, which tells me that this is a nonpolar molecule. It's made up of polar bonds. The CCl bond is a polar covalent bond. The difference is you have a polar covalent bond pulling to the left, a polar covalent bond pulling to the right, a polar covalent bond pulling up, a polar covalent bond pulling down. And everything is pulling evenly in the exact same direction. So because everything's being pulled evenly in all directions, you end up with an equal distribution. There's your technical definition of a nonpolar molecule. Real quick, let's do a couple of little definitions. First off is hydrocarbons. A hydrocarbon is a molecule that is exactly what its name implies. It is a molecule that is nothing but hydrogen and carbon. So, right there's your textbook definition. Hydrocarbon is a substance that is only carbon and hydrogen. Any numbers of carbons and any combination of hydrogens, C3H8, C8H18, C6H14, all of those are hydrocarbons. They have different properties, they have different uses. You don't have to know their uses, you don't even have to be able to draw them. That's the nice part of this. You just have to recognize it from a formula or a structure that if you have nothing but C's and H's, that is a hydrocarbon. And in our world, in the world that we're going to kind of live in, the simplified world, all hydrocarbons are always nonpolar. Now, don't go spouting that out to everyone you know, because that's not really true. But in our simplified little world, all hydrocarbons are going to be nonpolar. Essentially, there's an even distribution of hydrogens between all of your carbons and all of your hydrogens. Beyond that, don't worry about it too much. Just be able to recognize hydrocarbons from a formula, C's and H's, just C's and H's, and it will always be nonpolar. If there is anything else in your formula, even just one other atom, it is considered polar. So now you can tell polar and nonpolar based off structures, or in the case of hydrocarbons formula. We have one more key idea to talk about, and that's this idea of like dissolves like. So like dissolves like is a rule of hand that we kind of have that says nonpolar substances will dissolve other nonpolar substances, and polar substances will dissolve other polar substances. In other words, something will only dissolve something that is similar to it. So polar dissolves polar, nonpolar dissolves nonpolar. That's about as simple and straightforward as it gets. You don't really have to know too deep the nitty-gritty why. Okay, just remember that polar dissolves polar, nonpolar dissolves nonpolar. Well, what about ionics? Well, remember, you have nonpolar covalent, and then everything else beyond that is polar. Ionic is just super, 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 super polar. In other words, so uneven that one side basically steals those electrons, which means for argument's sake, an ionic bond is just considered another type of polar bond. So they will dissolve other polar substances. So polar, covalent, and ionic dissolve polar stuff, and nonpolar dissolves other nonpolar stuff. You're going to see some demos in class where we start using like dissolves like, but you can fill in these little tables using this idea of like dissolves like as well. First, you have to figure out the polarities of everything, so is something polar or nonpolar. So if we look at this big old table, I have 5 different substances: wax, baking soda, oil, water, and ethanol. Wax is a hydrocarbon, C's and H's, that's it. And what we learned earlier in the video, all hydrocarbons are nonpolar. Baking soda is an ionic compound. I have a metal and a bunch of nonmetals. And we just learned that for argument's sake, ionic compounds are considered polar. So I have something nonpolar, wax, I have something polar, baking soda. Let's look at my other 3 substances. Oil. There's a lot of different kinds of oil, but for simplicity's sake, we're going to say that all oil are made up of hydrocarbons, and hydrocarbons are going to be nonpolar. Water, H2O, you did an example of it earlier. You could flip back to that example and look at it. Or you can just kind of remember water is essentially polar. What we call water the universal solvent, it kind of dissolves everything given enough time, but when you just look at the molecule itself, water is polar. Last but not least, ethanol. I have C's and H's, so I know it's really tempting to be like, oh, that's a hydrocarbon, it's nonpolar, move on. But here's the thing you have to be very careful of. There's something else there. There's a single O, and that one single O is enough to make this a polar compound. It's C's, H's, and O's. That O getting thrown in there somewhere is going to disrupt the evenness of those electrons. So because you have something that isn't C's and H's, it's going to be guaranteed polar. So remember, like dissolves like. If something is similar to itself, it will dissolve it. So if I take wax and I put it in oil, both of those substances are nonpolar. They will dissolve each other. Oil will dissolve wax, wax will dissolve oil. But if I took that wax and I put it in water, well, wax is nonpolar, water is polar, they will not dissolve. Water will not dissolve wax. It does not happen. If I took wax and I put it in ethanol, it will not dissolve. Wax is nonpolar, ethanol is polar. Let's flip the script a little bit. Baking soda is polar. If I took it and put it in oil, I have baking soda being polar, oil being nonpolar, no dissolving. Like dissolves like. So something has to be like itself in order to successfully dissolve. Hopefully you've kind of seen the pattern at this point. Baking soda is polar, water is polar. 2 polar things, yes, it will dissolve. Baking soda and ethanol, both of those are polar things, yes, it will dissolve. So, quick summary, remember your 2 questions. Does my center atom have lone pairs, and is everything around it the same? That's going to help you determine polarity. Then remember, like dissolves like. 2 polar things will dissolve, or 2 nonpolar things will dissolve. Outside of that, you won't have any kind of reaction or change. So keep practicing, and come see us if you need any help.